Quick revision video on amines. So we'll start with some essentials. Amines are organic compounds derived from ammonia where one or more of the hydrogen atoms from the ammonia have been replaced by carbon chains or rings. Amines can be primary, secondary or tertiary. So a primary amine in general terms would look like that, where the nitrogen is bonded to one carbon group directly. Secondary, nitrogen is bonded to two carbon groups directly, and tertiary, 3. You can also see that in primary amines you've got two hydrogens bonded to the nitrogen, secondary, 1, and tertiary, none. In aliphatic amines, the nitrogen is attached to at least one straight or branched carbon chain or a non-aromatic ring, and I'll show you some examples of those in a moment. And in aromatic amines, the nitrogen is attached to a benzene ring, which is actually a phenyl group because the benzene's lost a hydrogen and is now C6H5. And finally, all amines can act as bases. That's because the nitrogen can accept an H plus ion using its lone pair, and it forms a coordinate or dative covalent bond. So moving on to naming amines now. So if you want to have a go at naming these, you can pause the video and then play on when you're ready. I'm also going to classify them as primary, secondary or tertiary, and aliphatic or aromatic. So the first one is methylamine or methylamine, as you might have heard in Breaking Bad. The next one, so we've got the longest carbon chain is 1, 2, 3, 4 long, so it's butylamine. This is carbon number 1 because the nitrogen's attached, the functional group's attached to the first carbon. So this is on carbon number 2. So putting that together, it's 2-methyl butylamine. Thought I'd include a skeletal one as well. So what have we got here? Well, the longest continuous chain is 1, 2, 3 long. So this is a propyl amine, but it's got an ethyl group on the nitrogen. So we call that N-ethyl propylamine. The next one, the longest continuous chain is 4 long. That's the chain on the right hand side of the N there. So it's another butylamine, but this time we've got two propyl groups on the nitrogen. So this is called NN-dipropyl butylamine. I very much doubt you'd have to name something as nasty as that, but that's how you would. So the one at the top here now, this is cyclohexylamine. And then moving on to the right hand side, we've got phenylamine, and we've got benzylamine or phenylmethylamine, you can call it. So essentially we've got a phenyl group, C6H5, on methylamine. So you've probably worked out the colour scheme. All the red ones are primary. You can see they've got that NH2 group in, or the nitrogen is directly bonded to just one carbon. The pink one is a secondary amine. Nitrogen's bonded to 2 carbons, and the one at the bottom, the blue one there, is a tertiary amine. So we'll look at some reactions now. So we'll start with the base reactions of amines. So remember we said on the introductory slide they can accept H plus ions using the lone pair on the nitrogen, and it forms a dative covalent or coordinate bond. And the product is an alkyl ammonium ion. So here's an example here. So this is cyclohexylamine. We saw that on the naming slide. That's just going to accept that proton, and it's going to become that, which is called a cyclohexylammonium ion, or you could represent it like that. So we'll do one more. There's ethylamine and H+, so it's going to become that, which is called the ethyl ammonium ion. So we'll look at salt formation now, which is very similar to what we've just seen, but we're going to bring the actual acid in. Amines can neutralize acids and form salts, and remember the definition of a salt is when the H+ ion of an acid is replaced by a metal ion, which is not the case here, it's an ammonium ion. So the example we're going to look at first is this one here. So there's that cyclohexylamine again. So remember what we said, the H+ from the acid is going to be accepted by the nitrogen, but also we've got a chloride ion as well, and so we get that salt there, which is called cyclohexyl ammonium chloride. So you can see how it fits the definition. This is now an ammonium ion and it's replaced that H plus ion there. So we'll look at one more, ethylamine with sulfuric acid, and the reason I've chosen this one is because of charges. So remember, the ammonium ions are 1 plus charge, the sulfate ion is 2 minus, so we're going to need 2 ammonium ions per sulfate ion, so the equation balances like that. And that salt's called ethyl ammonium sulfate. So we'll finish with the preparation of amines. So we'll start with aliphatic amines. So you do that by reacting a haloalkane with an excess of ammonia dissolved in ethanol. And I'll explain those 2 points as we go through this slide. So the example I'm going to use is the preparation of ethylamine. So you would use chloroethane and you'd react it with ammonia and you would get those 2 products. It's a nucleophilic substitution reaction. The ammonia is acting as a nucleophile. It can donate a pair of electrons on the nitrogen to the slightly positive carbon in the CCl bond. So I'll just show you that. So you don't need to know this mechanism, but you could be asked to suggest it, I suppose. So you can see there the nitrogen's donating that pair of electrons to that slightly positive carbon, and that's breaking the CCl bond, and that would be by heterolytic fission. And obviously that's going to ultimately generate this amine here. The ethanol is there to prevent any water reacting with the haloalkane. So if you think about, the oxygen has a lone pair on it in the water, and that could do the same as the nitrogen lone pair in the ammonia. And the excess ammonia prevents further substitution to secondary and ultimately tertiary amines. So if we just imagine that the haloalkane was in excess, that means that as soon as you've made your amine, so you can see the mechanism slightly changed, we've now got ethylamine is also able to react with excess haloalkane, and that would ultimately generate the secondary amine, where you've got 2 ethyl groups and 1 nitrogen and 1 hydrogen. So the final slide is looking at the preparation of aromatic amines. So we do that by reducing nitroarenes by refluxing with tin and concentrated HCl. Now, a very common mistake is getting the reducing agent wrong. So often students say that the reducing agent is NaBH4. That's the reducing agent for the reduction of carbonyls to alcohols, not for the reduction of nitroarenes to aromatic amines. So just be careful with that one. So the example I'm going to use is the preparation of phenylamine. So you would take nitrobenzene, react it with your reducing agent, and you would make your phenylamine and 2 moles of water. So notice that the reducing agent, for every nitro group that's reduced, you need 6 moles of reducing agent.